Hi, welcome to our other video on quadratic equations. This one's going to be reviewing solving quadratic equations by factoring, by doing that in a easy, not so easy, difficult manner, and then saying, hey, if it's not factorable, what do I do then? So we're going to solve by using the quadratic formula as well, and we'll have a problem to discuss those techniques. So the first thing we're going to do is factor this particular quadratic to find our solutions. Remember, finding the solutions is really finding your x-intercepts. So if the equation was equal to y, you'd replace the y with 0, and you'd end up with the equation that we have here. In this case, we have 2x squared plus 8x is equal to 0. There's no constant value, or c, so this one we can solve by taking out our GCF. We should notice, always first in factoring, to look for the GCF. The 2 and the 8 are both even numbers, and both terms have an x in it. So the GCF of this problem is 2x. When I pull out the 2x, I'm left with an x plus 4. And don't forget that this is still an equation, so I still need equals to 0. Now that I am in factored form, I can solve this because I know I can apply the zero product property, which states if I have two things multiplied together set equal to 0, that either the first part is equal to 0 or the second part is equal to 0. I've now created two linear equations that I know how to solve. The first one I solve by dividing both sides by 2, and 0 divided by anything is 0. And the second one I solve by subtracting the 4. Whatever I do to one side, I do to the other side. So I get my two solutions of x equals 0 or x equals negative 4. There will be two solutions because, as you recall, the graph of a quadratic equation is a parabola. Where it crosses the x-axis, there's two different spots. Here are the two different spots. In this particular case, it crosses it at 0 and at negative 4. Let's go through another example that's a little bit more difficult. This one looks like we already have factors, but the problem is we are not set equal to 0. In order to solve this and find your solutions, we need to make it into polynomials first so we can then set it equal to 0 before we can look to see if it's factorable. So on the left side we have to do a little foiling. Gotta love our foiling. Foiling, foiling every day. First term, outer, inner, and then last. Can you tell me how to pass this algebra class? And on the right side we use our distributive property. Cleaning up the left side, we have like terms which cancel each other out. And we have nothing else that's common on the right side. Now we have to set it equal to 0. Keeping your squared term positive, so I'm going to move the things from the right side onto the left side by switching our signs. Make sure that you are combining only like terms. I cannot combine an x squared with an x. It's two separate train cars. And our little choo-choo train here. And don't forget that once again we do have a right side of the equal sign. It doesn't go away. When you take everything away, you're left with 0. Now we look to see if it's factorable. Do I have two numbers that multiply to a positive 4 and add to a negative 5? Well, to multiply to a positive 4, I either have 2 times 2 or 1 times 4. Of course, with it being a positive 4, they are either both positive or both negative. If we add those together, we see that 2 plus 2 is 4, and 4 plus 1 is 5. Here I get my number of 5. To make it negative, I'm just going to have to put both numbers as negatives. So it factors to x minus 1 times x minus 4. Once again, FOIL to check. Absolutely no reason to get any of your factoring wrong because you can FOIL to check. We shouldn't have to check with the f because we chose x and x to give us x squared. We shouldn't have to check the last in FOIL, or the L, because we chose negative 1 times negative 4 to give us a positive 4. We only have to check the outside, negative 4x, and the inside, negative 1x, And sure enough, -4 and -1 equals -5x. It checks. Always good to do a check before we move forward. Now we have factored form. So now we can set the two factors separately equal to 0 to solve. This is called using the zero product property, saying that if two things are multiplied together and they're equal to 0, one or the other or both must equal 0. And we found our two solutions, x equals 1 or x equals 4. In our next example, we have a much more difficult looking problem. Here we have variables in the denominator. Now, in order to solve this, the first thing we want to do is eliminate our denominators. To do that, we have to find our LCD first. To find our LCD, the first thing we have to do is factor all of our denominators. X plus 5 has no GCF, and it's already x to the first power. So I can't reduce that any further. X plus 5, that quantity, is the factor of that denominator. Likewise, in our other denominator, there's no GCF in x minus 4, and x is to the first power, so I can't break that down any further. So those are both broken down into the simplest factors possible. 1 on the other side has a denominator also. All whole numbers can be written over 1, so it's the same thing as 1 over 1. Now, in order to find our LCD, I always go off to the side and I list off my factors. I list all factors of the first denominator. The factor is this entire quantity of x plus 5. That's why I put parentheses around it. Then I list all factors of the next denominator not already listed. X minus 4 is not the same thing as x plus 5, so I need to include that in my list. I continue for all of my denominators. My other denominator has a 1. 1 times anything is just giving us anything, so we don't need to add that in. Now that I've found my LCD, I multiply every single top part of my equation, both sides, by the entire LCD. So this 20 gets multiplied by x plus 5 times x minus 4. The x minus 4 gets multiplied by x plus 5 times x minus 4. Both sides of the equal sign, whether something's going to cancel out and be pretty for us or not, gets multiplied. So the 1 over here on the right side also gets multiplied by x plus 5 times x minus 4. Now some fun things happen in which we have some canceling that goes on. On the left side, the x plus 5s cancel out, and I'm left with 20 times the quantity of x minus 4. Minus, and here the x minus 4s cancel out, and I'm left with 1 times the quantity of x plus 5. Is equal to, nothing cancels on that other side, so I need both factors of x plus 5 times x minus 4. In order to solve this, we need to get rid of our parentheses. We do that by our distributive property. So the 20 gets multiplied inside to the x minus 4, giving us 20x minus 80. Careful on this next one. What gets distributed inside is the negative. Subtracting that quantity is subtracting every term in that quantity, so we have to distribute the negative in. So it becomes a negative x and a negative 5. Remember, subtraction is the same thing as adding a negative. So if you think of it as adding negative, and then that negative 1 is distributed inside. Equals, and on the right side we have to FOIL. That's the procedure for multiplying a binomial times a binomial. Each term in the first set of parentheses is multiplied to every term in the second set of parentheses, called the FOIL method. First, outside, inside, last. Foiling, foiling every day. First term, outer, inner, and then last. Can you tell me how to pass this algebra class? Okay. Now we clean up by combining like terms on both sides. On the left side, I see that I now have a 20x minus x, which is going to make 19x. No switching of signs because we kept them on the same side of the equal sign. I also have a negative 80, the sign in front of the term goes with the term, and a negative 5, which makes a negative 85. Or adding a negative 85, which is the same thing as subtracting 85. On the right side, I also have some like terms from my FOIL method. So I get x squared. Oh, did you notice my mistake? It's supposed to be a plus 5x. I was too busy singing, I guess. Negative 4x plus 5x is a positive 1x, and then minus 20. We don't necessarily put the 1 in there, because 1 times anything is anything. But the 1 is there because 1 is the god of Mathland. He, she, it is always with us. Now, we have an x squared. To solve an equation that has an x squared, we get everything to one side of the equal sign. I always keep my x squared positive because it's a whole lot easier to factor later if it's factorable. Gets us really confused if we have a negative x squared. So I'm going to move both terms from the left side onto the right side. It's a positive 19x, so I'm going to subtract 19x. It's a negative 85, so I'm going to add 85. Now remember, when 19x minus 19x is 0x, it cancels out, and the same thing with the negative 85 and a positive 85. But I still have a 0 to represent the left side of the equal sign. This started off as an equation. It will be an equation all the way through. X squared, a positive 1x minus 19x is a negative 18x. Negative 20 plus 85 is a positive 65. Now I have to see if it's factorable. Are there two numbers that multiply to a positive 65 and add to a negative 18? Well, let's go through our possible solutions here. I know for one thing that since it's a positive 65, both signs have to be the same. I know that I have to have an x and an x to get my x squared, and for both of them to add to a negative, they both have to be negative. So now I go over to the side and say, 65. What times what is 65? And I say, well, since 65 ends in a 5, I know that 5 goes in there. How many 5s go into 65? Well, 1 5 goes into 6 with a remainder of 1. 3 5s go into 15. Oh, look, 5 and 13 add to 18. So my factors are going to, or my numbers in here are going to be 5 and 13. Still equal to 0. Now that I have it in factored form, I can apply my favorite property, the zero product property, which states that since I have two numbers multiplied together equal to 0, either the first number is equal to 0, or the second number is equal to 0, or they both equal 0, if they were the same. Then I solve by doing my opposite steps, my inverses. Add 5 to both sides on this problem to get x is equal to 5, and add 13 on this one to get x is equal to 13. Now, because we started off with a rational equation, our variables were in the denominator, we have to double check our solutions. If I replace either of my solutions in for x, and the bottom simplifies, or the denominator simplifies to 0, that can't happen in Mathland, and therefore it would not be a solution. My first solution was 5. 5 plus 5 is 10, and 5 minus 4 is 1. So I'm okay on that one. If it was a negative 5 plus 5 would make 0 and implode upon ourselves in Mathland, and therefore it would not be a solution. But since our solution was a positive 5, we're okay. Our other solution was x equals 13. 13 plus 5 is not 0, so we are okay on that one. And the same thing on this side. 13 minus 4 would give us a 9 and not 0. So that means that both answers are going to work. So my solutions for this equation are x equals 5 or x equals 13. Now, we just went through 3 examples of quadratics that are factorable. We did kind of learn about that a few weeks ago when we were learning about factoring. But what happens if the quadratic equation given to you isn't factorable? Is there no solution? I wish that was true, but no. It means that we have ugly looking equations, ugly solutions to this, where the x-intercepts are not pretty numbers per se. We can still solve it. We can solve every quadratic equation by using the quadratic formula. It's not the prettiest though, and that's why it's good to know if the equation is factorable, because we'd much rather solve it by factoring than using the quadratic formula. But if your quadratic is not factorable, we can always solve it by using the quadratic formula. The quadratic formula is x is equal to the opposite of b plus or minus the square root of b squared minus 4ac all over 2a. In order to use that equation, though, we need to make sure that our equation is set up properly. The first thing we have to do is set the equation equal to 0. Then we identify a, b, and c, making sure that the sign in front of the term goes with that term. And then we simply plug it in, plug it in. So here I have an equation, 5x squared minus 8x is equal to 3. First thing we need to do is set this equation equal to 0. Currently, it's equal to 3. So, to set it equal to 0, we subtract 3 from both sides. Now remember, you can only add or subtract like terms. Terms with the same variable raised to the same exponent. 3 is not like an 8x or a 5x squared. So we just add our choo-choo train. Highest exponent first, so the 5x squared, minus the 8x, minus 3, and we still have an equal sign, so it's still going to be equal to 0. Now that I have my equation set equal to 0, I identify my a, b, and c. I like to do this to make sure that I keep things organized and that I don't lose any signs. A is always the number in front of x squared. That's why we put it in the standard form, so we can identify our coefficients left to right. So our a is 5, our b is negative 8, and the c is a negative 3. Now that we have our a, b, and c, we plug it in, plug it in. To help us retain the quadratic formula and to make sure that we're understanding it, I strongly suggest that you write it down every single time, making sure that you're copying it from the book where you know it's written correctly. X is equal to the opposite of b plus or minus the square root of b squared minus 4ac all over 2a. If you also are stating what you're writing down instead of just copying it, whether you sing it or not, it's good to state it out loud or at least go through it in your head so that you make sure that you plug the correct numbers in the correct spot. So in the formula, we are finding x, that's why it's called the formula to solve this. X is equal to, and it starts off with the opposite of b. Well, if b is a negative 8, the opposite of a negative is a positive 8. If b was positive, the opposite of that would be negative. So it just switches the sign on your b. Plus or minus the square root of. Now, we're squaring our b. Most students just write in negative 8 squared, and then they get the wrong answer, because this is not squaring the negative 8, this is squaring 8 and then taking the opposite of it. If you plug that into most handy dandies, you're going to get the wrong answer. You need to be smart and realize that when I square this b value, I will get a positive answer 100% of the time. So really, the negative 8 is necessarily in parentheses to know that you're squaring the negative along with the 8, not just the 8. So that b squared portion will be positive 100% of the time. If it's not, you did something wrong. So make sure that we're working smarter, not harder. What I say in my class is that if there's one time in which you can lose a negative, that would be the spot. Because if you write 8 squared in there instead of negative 8 squared, you're going to get the same answer. And it'll be correct. Continuing on, minus 4 times my a value, which is 5, times my c value, which is a negative 3. All over, now that means all of this, even the 8 in the beginning, has the division line under it. 2 times my a value, which is 5. Now we simplify. I'm running out of space, so I'm going to rewrite this on a new page. So here's our same problem. X is equal to 8 plus or minus the square root of all that other stuff all over 2 times 5. So our order of operations say that we would simplify inside parentheses. A radical sign like this is an assumption that everything underneath there is in parentheses. You have to simplify all of that first. So we're going to have our 8 plus or minus the square root of. Negative 8 squared is going to be a positive 64. Now that I'm in a different term, I can do this multiplication at the same time as well. This is where some students struggle with, oh, is this a negative or is it a subtraction? It's one or the other, but not both. I like to think of it as a negative because subtracting is the same thing as adding a negative. So I rewrite it like this, plus a negative. And then actually I go through and I say, well, wait a second. How many negative signs do I have in this multiplication? It's a negative 4 and a negative 3, so I have 2 negatives. Every 2 negatives being multiplied together makes a positive. So this result will be a positive. And now I can just multiply my numbers. 4 times 5 is 20. 20 times 3 is a nice number, like 60. All over 2 times 5 is 10. Don't jump ahead. Continue on with your simplifications. Our next step is going to be to add those numbers underneath the radicals. Now in this case, we might be tempted to cancel the 8 and 10. We can't do that. That's illegal in math land because the 8 is being added or subtracted, technically both, to that square root, which means that it's a term. We cannot cancel terms in math land. We can only cancel factors. Terms are being added or subtracted, factors are being multiplied. In addition, we can't reduce anything with the 124 because that's a radicand. A radicand is a number underneath a radical sign. Numbers underneath radicals are irrational numbers. Numbers that aren't underneath the radical are rational numbers. We can't cancel a rational number with an irrational number. That's just plain silly. However, we did learn in the last chapter how to simplify radical expressions. 124 is not a perfect square, but it has a factor that is a perfect square. So we want to use that to simplify. And the first thing I always do when looking for perfect squares is look to see, is my number even or odd? Since 124 is an even number, I hope that 4 goes in there evenly. 4 is the smallest perfect square that's even. So I go and find out how many 4s are in 124. Well, 4 goes into 12 3 times with no remainder, and 4 goes into 4 once. So 4 times 31 is 124. Now I recognize that 31 is a prime number. I never came up with 31 when I was doing any of my multiplication tables, so the only way I get 31 is 1 times 31, which means that there is no other perfect square in 124. 4 is the largest one. So now I'm going to replace the 124 with 4 times 31, because 4 times 31 is the same thing as 124. So I'm not changing the value of this radical, I'm just changing what it looks like. Now there's a law with radicals that says, hey, if you are multiplying or dividing, and only multiplying or dividing underneath a radical, you can write that as 2 separate radicals. So I'm going to rewrite that as the square root of 4 times the square root of 31. Still multiplication. If you need to, put your multiplication dot in there. Do not use the cross for multiplication, as this is algebra. And now we have the square root of 4. We can simplify the square root of 4. So now we have x is equal to 8 plus or minus, the square root of 4 is 2, we didn't take the square root of 31, so it stays the square root of 31 all over 10. We're almost there for this problem. Now we have to reduce. Once again, I can't reduce the 8 and the 10 because the 8 is being added and subtracted to the 2 square roots of 31. I have two terms on top. The one is the 8, and the other term is 2 square roots of 31. But I do notice that 8 and 2 are both even numbers. As they are both even numbers, I have a greatest common factor of 2. So I can pull out the greatest common factor of 2 from the top. And so it would be 2 times the quantity of 4 plus or minus the square root of 31 all over 10. If you wish to put the 1 in front of the square root of 31, you can do so. But once again, 1 times anything is anything. Now the 2 that I pulled out in front is a factor. So I can cancel that factor of 2 on top with the 10 on the bottom. 2 goes into 2 once, 2 goes into 10 5 times. 1 times anything is anything, so I get the answer of 4 plus or minus the square root of 31 all over 5. Those are my two solutions for this equation. What do I mean two solutions? Well, the first solution is 4 plus the square root of 31 all over 5, and the second is 4 minus the square root of 31 all over 5. The plus or minus is a symbol that allows us to write those two answers compactly, since they have everything else the same in position of that answer. The only change is that one time you're adding and the other time you are subtracting. Now, we oftentimes struggle with taking out that greatest common factor. There is a shortcut that if you think of the Three Musketeers, you can do. The Three Musketeers, sure, it's all for one or one for all, right? So in this step beforehand, we once again notice that 8, 10, and now the 2 are all rational numbers in 3 different terms. The square root of 31 is part of this term, but it's the irrational portion. Since all 3 terms have a rational portion that are similar, what you can do is cancel all by the same number. It's all 3 of these or none. And that's why it's the Three Musketeers. It's all or none. And you reduce all of them by the same number. Since they can all be reduced by 2, you can do so to come up with your answer. 2 goes into 8 4 times, 2 goes into 2 once, 2 goes into 10 5 times, giving you the solution we came up with, 4 plus or minus the square root of 31 all over 5. Once again, if you need to, you can write those as the 2 separate solutions. The one solution is 4 plus the square root of 31 all over 5. And the other one is x is equal to 4 minus the square root of 31 all over 5. Apparently I had a dyslexic moment up there. Those are the 2 solutions, which you can write it compactly using the plus or minus symbol if you'd wish to. Now those are called exact answers. Yes, I'm almost done. These would be your exact answers for this problem. Once again, you can write it either way. Leaving it as a radical gives you that exact answer, no decimal approximation. However, sometimes the problem asks to find the decimal approximation. How are we going to do that? Well, let me show you. So if the directions ask you for decimal approximations rounded to the nearest hundredth, you can plug this into your calculator at this point. Now, be careful in which you have to remember that when something's written as a fraction like this, that it's this entire numerator that's then divided by 5. So depending on the type of calculator you have to be very careful as to how you type this in. If you have a 2-line display calculator or a graphing calculator, which wasn't required for this class, but if you happen to have one, you put it in parentheses as such. And you can put in your parentheses, 4 plus, and then you put your square root symbol. Now, if you have a two-line display calculator, like the TI-30X2S, when you put in the square root symbol, it automatically puts an open parenthesis in there. Yeah, that's key to look at, because after you type in your 31, you're going to have to close the parenthesis, which only closes the square root. That parenthesis that was underneath there opened up the square root. This parenthesis closes the square root. You would then have to include another parenthesis to close out this entire top. And then you could type in divide by 5 and your equals. If you do not have a two-line display calculator or a graphing calculator, I would suggest putting in the 31 first, then hitting your square root symbol. Because in a single line display calculator, just a scientific calculator, it does things backwards. You have to put in 31 and then tell it, find the square root of that. So you'd put in the number 31, then hit the square root symbol. Then you would add 4 and hit equals. Then divide by 5. When you do that, you should get some number that fills up your whole calculator screen. That's something like 1.91355528, etc. Okay. So make sure that you play around with your calculator until you come up with that answer. Now in this case, the directions say to round to the nearest hundredths. Hundredths, the number 100 has 2 zeros on it. So that tells us that we need 2 spots to the right of the decimal point. That tells me I look at the third spot. If that is 5 or higher, I round the 1 up to a 2. If it's 4 or lower, I keep the number the same. It's 4 or lower, so this would be 1.91. If I was rounding to the nearest thousandths, I'd have to look at the 5, which would round the 3 up, and that would be 1.914. Just as a little review from rounding. I do believe there's more directions. It's either on page 23 or 25 of your book. But remember, that's only one of your solutions. Here's your other solution. We do not just stick a negative sign in front. We get a whole new number when you use the subtraction. Same idea though, if you have the two-line display calculator, this is key. If you have the two-line display calculator and you had typed this in correctly, all you would have to do is arrow up on the right top of your calculator, and it'll go back to what you just typed, and you can move your cursor over to this plus sign and hit a minus sign on top of it. And then you'll automatically, and then hit equals, and you'll get your new answer. So you can edit it without having to type all that in. If you have a single line display calculator, as stated before though, you have to be extra careful, because you're going to type in your 31 and then the square root. But you need to make that negative, so then you would have to hit that plus or minus button to make the square root of 31 negative. Then add 4 because the 4 is positive. Remember, we can't switch the order of subtraction. So plug in 31, hit your square root button, hit the plus or minus button that makes it negative, and then add 4. Hit equals, and then divide by 5 equals to get your answer. Make sure that you get familiar with your calculator to make sure that you get the correct answer. Once you plug that in, your calculator should give you negative 0.3135528, etc. Once again, make sure that you follow the directions and round accordingly. It said to round to the nearest hundredths, so my answer here would be negative 0.31, as the 3 once again keeps the 1 the same. So my two solutions, because it asked me to round to the nearest hundredth for this problem, x is equal to negative 0.31 or x is equal to 1.91. That's how you would find a decimal approximation for this quadratic equation. Hope this helps. Good luck.